Yeah.
Yep. Good morning, everybody. Welcome to the final presentation of Jerry de Vos, the last part of his student time here. Just another 1 or 2 hours to go, and then he's not anymore a student. And Jerry is a very special person, as you might know him all. I had the opportunity to get to learn him doing one of the projects in our school called Advanced Embodiment Design. And I see also some of the teammates from that time also on Zoom right now. And then he already came out as a kind of very creative person who likes to go in depth, play with technical things, but also think about impact, making impact to make it a better world. And then I had to look to work a little bit more with Jerry, not only in our Advanced Embodiment Design, but he also became even part of our research team temporarily as a kind of prototype builder, designer. And together with him, we developed a device which we sent even all the way to Gabon in COVID times to do the test there over in the field. But Jerry, of course, has even much more things to work on. And what I learned with him is that he also likes to work on upcycling plastic, for example, working with precious plastics, but also likes to work a lot in the global south, in different parts of the world where the resources are very limited, but still to see what can we do with design and technology, again, to make it a better world. And I think that is where it came up to the final project of Jerry, where all the things came together. Smart diagnostics, upcycling of plastics, and the global south. 3 parts, which are, and maybe also open hardware as a last part there. All those elements he wanted to challenge to bring that together into one project of 20 weeks. And that's what we're going to see right now in the coming half an hour. And I can tell you already, I feel a little bit not like on a graduation presentation here, but I feel like I'm in a scientific museum here right now, because Jerry built up here a whole show. So something special will come up. So prepare yourself for the final presentation of Jerry, titled Plastic Identification Anywhere. And my name is Jan Karel Diel, JC Diel. I was the chair of the supervisory team. I did it together with Professor Jo van Engelen. Jo, can you wave your hands? Yeah. And but most of the work, of course, has been done by the candidate himself, Jerry. So the floor is yours.
Thank you for the kind introduction, JC. So JC will be in the same room in the background. If anything happens, then at least he will still get the full experience. I think we can get started. I will start sharing my screen. So hopefully now everybody can see the presentation enlarged and me as a small avatar on the right-hand side. Yeah, okay, I get a confirmation. It's nice. Welcome everybody for joining. And as a side note, please mute yourself. At the end, there will be questions, and then you can unmute yourself and raise your hand and ask any questions. Just to streamline the process for now, enjoy the ride. As introduced earlier, my name is Jerry de Vos, and today I will be presenting my master thesis on the topic of plastic identification anywhere. I will tell you what led up to the project, what all the details were within the project, and lastly, also maybe a hint for what is in stock for the future. So let's dive straight into it. I would like to start with a small story. So imagine it's February, it's a cold winter day in the Netherlands, but you're heading out to the Maldives for 10 days. So let's think. What do you expect? Probably white beaches, palm trees, and a blue ocean. Probably something like this. Well, when I went in 2019, what I found was this, Tilafushi. It's the garbage island of the Maldives, and this is where all the trash is moved from all the small islands just to one island. And in the end, there was basically no real Maldives experience. So in the back, you could still see a little bit of the white beaches and the blue ocean. But most of it was just one big island with all this mixed trash. And if there was a storm or if there was heavy rainfall, all of this plastic just slips into the ocean. There's just a few meters of barrier between ocean and landfill. So I was, as you can see in the picture, kind of upset about this. And what I found, what people told me was that this is not the only place in the world where it's like this. I started to research this, and if you look online, there's a lot of places around the world highlighted in dark red where plastic waste management is low, and a lot of the waste is mismanaged on open landfills, or it just slips into the oceans through rivers, for example. So I wanted to do something about this. And what I found was that, most of this is highlighted in low and middle income countries or the global south. And even though we had great ambitions for 2020, we still see that every year we produce more and more plastic. And also the amount of plastic polluted is still rising, let alone a global pandemic that increases the use of single plastic products drastically. So I started wondering myself, like, what can I do as a designer to improve plastic waste management? I knew that the biggest impact that was possible would be in the global south. So I started to interview people. I started to research this. And I tried to do this at various places within the global south to see what people want and how their recycling process looks like. And what I found was that by far the most difficult stage in waste management or in plastic recycling is this part. Finding a product and determining what type of plastic it is so that it can be properly recycled. Different plastics have different melting temperatures, different properties. So if you want to make new products out of it, it needs to be pure. Just like with metal or with glass, you sort it based on type. And this is, in low and middle income countries, a very manual process. A worker needs to find the label and put it in a correct bin. And it takes a lot of time, and therefore recycling is not always viable, and it just ends in the landfill. And then I started comparing to places where the amount of plastic waste is relatively low. And what I found is that, for example, in Western countries, we use a lot of sensors to detect types of plastics. And for example, this is such a sensor. It's the RIRI meter project. And this is able to identify different types of plastic. So my question became, how can I combine these kinds of sensors with low and middle income countries and be able to implement it there so they can recycle better and faster, making it more accessible for anyone? So I started researching, I started prototyping, and I started with simple prototypes, just a cardboard box with some sensors, and then a bit more complex and more testing, and tried cutting PCBs in half, and then more testing and more testing. And finally, today, I can present the plastic scanner. So this opens. This plastic scanner is able to identify over 75% of all the plastics used around the world. The most common plastics used are PET, HDPE, PVC, LDPE, PP, and PS. And how this works is that it measures the reflectivity of IR light. So if you shine different wavelengths infrared light on a product, and you measure the reflection, you see that there are small differences within the plastic. Just with a visible object, if you shine light on it, it reflects the color of the product. So you know the button is red. You can do the same with plastic with infrared light. And then it reflects what type of plastic it is. So I made this, and this was the solution, right? Now I could identify plastics anywhere. Well, not really. When I started to ask more and do more interviews and talk more with these people, I found that it requires quite a bit of differences between the places to implement this. They have different needs, and Some have a big budget and want it very precise, and some have a small budget and just roughly want to sort plastic. So one simple product would not suffice. All the plastic will not suffice and make it possible to sort plastic anywhere. So I went back to the drawing board, and what I found was that for plastic recycling, and in order to make this really a versatile product that can be used anywhere, there are three important factors. One is context variation, so making it possible to adapt the plastic scanner to the context in which it's used. Local manufacturing, making it possible to build such a scanner locally, because the resources differ due to this context variation. Also, the tools available to build such a scanner differ, and you want to be able to have people make the product nearby, and also start to improve it with the tools that they have. And lastly, an important factor for me was open development. The knowledge that I have about plastic recycling and infrared spectroscopy is limited. So I wanted that to be able that people who are experts in these fields can contribute with their knowledge and improve this project over time so that it really starts to grow. And based on these three factors, I made sort of small modules that can be combined together in order to make the ultimate plastic scanner that fits to your context, and really making it versatile to implementations anywhere. Firstly was the breakout board. This board is able to measure the different wavelengths IR. So it has all the components, LEDs to shine the wavelengths, a sensor to measure the reflection, and then some ICs to basically measure how big this reflection is and communicate it over a standard protocol. I built it in such a way that it has relatively big components, so you can solder it by hand, or you can automate the process by a pick and place machine, so you can scale it up more easily. Everything is just fit on one side, so it's easy to build. And basically, this is all you need in order to scan plastics. But then you still need some brains and some other components to implement it in your process. So luckily, there still is the handheld scanner, and all my work was not for nothing. So this is basically the embodiment and an example of how such a breakout board could be used. It houses the breakout board, but also some other components to really make it portable. So, for example, the green part that you see is a small Raspberry Pi. It's a small computer, and that can take this measurement data and transform it into a human readable output, which is the type of plastic. It also has some other components like a button and a screen for input and output, and a battery and a charge system in order to make it portable and rechargeable. But I also wanted to ensure that people all over the world could actually build such a product. And sometimes it can be difficult to source the components, or you're not sure if you have the right components. So that is why I also wanted to provide a kit. This makes it as easy as Lego to build a breakout board. And it has all the components sourced for you and easy steps that you can follow, test along the process if everything works as expected, and then at the end start to implement it in your plastic process. And these are all very tangible aspects, so some things that you can hold. But I found that also it's important for such a project to have some other aspects which really help to grow a community around this and to start involving people around the world to have this implemented in their plastic recycling workspace, but also to make it possible to do contributions. So for this, I built a website, plasticscanner.com. You can visit it at the end of the presentation. And this shows all the different aspects of the presentation of the product and also possible implementations. So it can inspire people on how they can use it or how they can modify it to their needs. Another crucial thing was this open development. So I shared everything under a GPL3 license, which is an open source license that makes it possible for anyone to reproduce such a product. All the documentation is on wikifactory.com. And this makes it possible for others to analyze how the product is working and to verify it's working, but also to make small contributions. You can just suggest small edits, and then it can be implemented and improved over time. And lastly, there's one final crucial step, and that was having these brains that change the measure data into a output, what type of plastic it is. So for this, I used machine learning, and you have on the left side the 4 arrows that input the different measurements from the wavelengths. And then on the output, based on previously known samples, it is trained and it outputs the type of plastic. So what I'm presenting today is not just a single plastic scanner, but it's more of an ecosystem, a framework with different modules so that people can adjust it to their needs and have it implemented in their plastic recycling workspace. And this makes it possible to do plastic identification almost anywhere around the world. Whether it's just people want to scan plastics with a mobile device, or whether it's, for example, the ocean cleanup who wants to identify types of fishing nets. But it could also be implemented in small factories to already sort types of plastics. So it's a much more versatile solution that can be adjusted to your needs. And this should make it possible to have a more broad impact. So for example, here you see Manduku. I think he's also somewhere in the chat, hopefully, if he had internet. And he has a small recycling workspace in Kisti. And every day he collects plastics, but then he still needs to sort it. And he is super eager to try such a plastic scanner and to get started and have it implemented in his recycling workspace. And all of this makes it possible to accelerate plastic sorting. It makes it possible to process higher quantities of plastic, and that makes it more viable. It also makes it traceable, the amount of plastic that you have, and the purity, so that in the end you have a higher valuable material, since you can prove that it's consists out of 87% PP, for example. And all of this makes plastic recycling a lot more economical, viable, while reducing the amount of plastic that ends up in the ocean. So this is good for me, for humans, but also for my holiday in the Maldives. I hopefully next time I can actually go to the white beaches and there isn't such a big landfill anymore. So today it's more of a ecosystem framework, and now it's up to me, up to you, and up to anybody around the world to start playing with this, implement it, and improve it over time. It is built in such a way that it can be easily improved and new versions can be released. Now, lastly, probably this is the part what you all have been waiting for. Let's see if we can have a demo. It turned out that I'm not a fully electrical engineer as I hoped I wish. So I have been building this plastic scanner, but somehow there were some difficulties with the breakout board, and it can blink the different LEDs, but it's not as reliable as I wished it would be. So for that, I built this lab prototype, which uses the RIRI meter, which you saw earlier, and a Raspberry Pi to do the processing, a small screen and button. And we can see if we can connect this up and start scanning some plastic. So for this, I will stop sharing my screen and add an extra camera view. So let's see if we can get it up and running. Then hopefully, yes, now you can see the presentation. Hopefully it doesn't blink too much. So as I mentioned earlier, there is the Raspberry Pi. This does basically all the processing of the measured data. And then there's the RIRI meter that can actually measure the different wavelengths LED IR light, and a screen and a small button. This just needs a few minutes to boot up, and then hopefully the screen will turn on with an introduction, as it did now. So it's a bit difficult to see, but I will try to put it a bit closer. And luckily, I brought some plastic samples with me, otherwise it would be a bit useless. So here you can see the scanner. So we put a sample on top, and then we press the button. It flashes a light, and it starts to do the measurement. And then based on this, you see the output, which now might be flickering, but for me it's not. And you can see that it thinks it's 95% certain it's HDPE, 4% certain it's PP, and 0% certain it's PET. So you can very certainly say that this is probably HDPE, which is often the case with bottle caps. Here we have another sample. So we can also press it on there, press scan, it does it again. And currently with this one, it's a bit less certain. So it gives a maximum of 74%. So let's see if we can try it one more time. And here you can see that well, it's really difficult to see clearly. So it's pretty certain that it's PP 99%, HDPE 0%, and PET 0%. And if you look on the product itself, there is a small recycling icon, which actually indicates that it is PP. It also has the features that you would expect from PP. And lastly, we can also try to scan a PET bottle. And with this one, it's pretty certain it's PET, but at the moment it's just trained on 20 samples of each of the types of plastic. So the more samples collected and scanned, the better the prediction will become. So now it still says 72% PET, which is, yeah, most likely still is PET. And then the RIRI meter, the breakout board compared to the RIRI meter has some future improvements where it can modulate the light and filter out external light. So you're certain that the infrared light that is shown on your, that is reflected from the sample is from the infrared light. And this should also make it possible to improve the readings and have a more versatile scanner that can scan more types of plastic. So that was the demo. Later, at a later point, we can still see if we can scan more objects if there's time. Let me share my screen for the last few slides. And then it's time for questions. So I hope that you guys are as excited as me. Oh, sorry, it's still on the wrong camera. Let me see how I can swap camera. Okay, so I hope you're as enthusiastic as me about this project. And for this, I made a 2-minute video that entails everything about the project and that informs you about the different things you can do to incorporate this into your plastic recycling workspace. So I will share a link in the chat to the link of this to this video. And yeah, feel free to share it around or have other people know that this project exists and that they can start to help improve the project and implement it in their plastic waste management. So that was basically it for me for now. If I can change my slide. Yeah. So I think now it's time for questions. I will firstly give the floor to JC.
Well, I have to make a lot of noise on my own here. Yay! Thank you, Jerry, for this really great presentation, which started with this beautiful dream of going to the Maldives, the blue ocean and the green and the beaches you were talking about, but then making us also aware about the reality of the state of the world and all the challenges we have with, amongst others, plastic waste. And you also really nicely showed how you have been working as an industrial designer by first talking to people, understanding the real needs, what are the challenges they are encountering all over the world in the plastic recycling world. And then to see like, how can we use smart technology, which we use here in the Western world, also in low resource settings in the global South. And then to come up with this whole idea of, let's say, how can we make it open source, open hardware, but also how can we do it with context variation, that we don't make a product which doesn't fit with the local context so it can be adjusted. And then to develop a hardware product, but not only then you stopped. No, you never gave up. You continued by developing even the algorithm with machine learning. And the demo showed us that it's always working. And last but not least, then again, it would not stop with you with hardware and software. Then you also make this beautiful plan how to hand it over to the rest of the world and to engage everybody to make this a next step in plastic recycling or plastic upcycling. So yes, indeed, I am at least impressed. We will go to the Q&A. For that, I will run away from this camera and I will go back to my laptop and see what kind of questions have been put into the chat session. So if you have more questions, put them in the chat session. I see Jerry is already looking through it. So maybe then the easiest is that I give it back to Jerry and that he picks out, or what do you want me, Jerry, to read out the questions to you? Or
yeah.
Okay, I will sit there and I will read out the questions to you and you can stand behind the camera.
Yeah. I also have a laptop here with questions, so I can read along and try to answer your questions.
Okay, Manuel Garcia, he asks you, hi Jerry, can you say something about the accuracy of the machine learning algorithm?
Yeah, totally. Let me see if I can get the slides. So I think there's more questions about the machine learning algorithm, and basically what I used for the machine learning algorithm is Google TensorFlow, and this is an open source project that enables anybody to implement machine learning in their project. And this is currently a supervised machine learning model that clusters on the type of plastic. So I can give you a small overview on how it is trained, and then you can also see the decrease of the errors that it's making. So you should now be able to see my screen. So basically what you do is you import different types of known plastics. So you set up a small database, you scan a lot of plastics around you, and you give it known values. So for example, with the bottle caps, you scan a lot of the bottle caps and you know that these are HDPE. And then what you can do is you can train the algorithm. So here you let it train for 600 times. And then you see over time, it decreases in the amount of losses that it makes and errors. And you also see a training or a reduction in the mean error. And here, for example, you see you split the data in training data, validation data, and testing data. And here you see some testing data. So you give the testing data to the machine learning algorithm, and it thinks, it's 98% certain that it's the first type, which was PP. And then you compare it with the actual input, and it turned out that, yes, it was PP. If you graph this, you see this. You ultimately want to see everything either a 1 or a 0, because then it's super certain. But there are also some values in the middle. But training this with a bigger data set with more samples should make it possible to make it more accurate. Then this trained model is exported and transferred to the Raspberry Pi, which is in the device. And this makes it possible to also exchange these models around the world, which was another question. But currently, I'm not certain on if this is possible, because if people build the sensors themselves, they might have small variations in the types of LEDs or in the build quality. So it could be that you could import this big online data set, but then need to calibrate it for your personal breakout board. So this would make it possible, for example, to import this pre-trained model, but then you need to scan like one Coca-Cola bottle because we know it's PET, and one shampoo bottle because, for example, it states that it's ATP. And that way, it should be able to make it more versatile and implementable at different places at the world, and not everybody needs to build their full online database. I hope this answers your question. I don't know if there's more questions directly related to machine learning.
No, thank you, Jerry. So I think Jan Fabian had the same kind of question. He was about the machine learning. So let's go to Miles Pennington. Hi, Jerry. Great idea. What is the smallest piece of plastic it could work on? So how small pieces of plastic can you work with your device?
Yeah. Thanks for this question. And in the beginning, I hopefully said good morning, but maybe it's good evening for you. Currently, the size of plastic is limited to how close the different wavelengths LEDs are placed together. And this is at the moment a 18 millimeter diameter hole. So it's also the goal it's also mandatory to measure items that are this size. I also do have actual ocean plastic from the Great Pacific Garbage Patch, and I'm planning to test with this in the future to see if it can also do smaller plastic flakes. But at the moment, just to be sure that there's no external light, we only scan objects that are 18 millimeters or bigger.
Thank you. Well, the other things I think you already answered. The other question was like, are there any plans on providing a centralized database for scanned plastic samples? Or part of it already, isn't it?
Hi, Armin.
And then Dolores was asking about, hi, Jerry, thanks for the nice presentation. You mentioned that it can recognize 75% of the plastics, the most common type. I was wondering how the scanner handles uncertainty in identifying the type of plastics. For example, occurrence of type 1 and type 2 errors or an I don't know message. So currently for this demonstration, I made it rather easy for myself, where I had known samples and I only scan when there is a sample in front of the sensor. But yes, afterwards you also want to be able to scan different objects, objects that are known unknowns, and also make it possible to state a prediction that it says, I am too uncertain about this prediction, so please scan again, so that it's possible to give a rejection to actually really be certain about the type of plastic. Thank you. Joseph Kiat, he asked, a very important question. What is the expected total cost of material? So that is going to cost.
Important question. I forgot to mention this in the presentation. Luckily, I should have a slide on this. if I can. I have two overviews of costs. If you want to build a breakout board with all the components on there, that will set you back around 175 euros. Most expensive parts are these discrete wavelengths LEDs. The other parts are more commonly used. And if you want to then implement this into a handheld scanner, you firstly need the breakout board, 175 euros. And then all the other components inside of this make it a total of 260 euros. So that includes a 3D print, screen, Raspberry Pi, cables, connectors, battery, all these kind of things. Good question.
And do you expect that in the future this price could go down, either by making it more in batches, or that you expect that electronics will go down in price in the coming years?
So me and Armin have been in contact with the manufacturers of these discrete infrared LEDs, and they can already upfront state that if bigger quantities are ordered in one go, so if we, for example, make 100 of these kits, then the price goes down significantly, around 10-fold. But also we expect that in the future, these LEDs will be more of a commodity, and more suppliers will be available, which reduces the price.
Thank you. Well, one of the questions you already answered, but I just mentioned it. Akil was asking, hey, Jerry, great work. Does machine learning modules needs to be retrained if someone tries to build from locally sourced components? Well, you already explained that. Huh?
Yeah.
Want to add something still on it?
So maybe something that's still good to add is that over time, these models can be improved and new versions can be loaded. All the Raspberry Pis now have wireless communication. So it's very easy to have an over-the-air update where you import a new trained model and then makes it possible to have better predictions.
Thank you. Well, Natasha says, Jerry, would like to see the white beaches back. Me too. Do you believe recycling on itself is enough to solve the plastic pollution problem? So the scanner and recycling, is that the only thing we have to do?
I wish this was like an ultimate solution, and now this would solve most of the problems, but I think it's only a very small part of the solution. In general, just try to reduce the amount of plastic that you use on a day-to-day basis. If everybody would do that, that would be already very significant benefit. And yeah, we still have to deal with the plastics that are already existing around the world, which is now 7.8 billion tons of plastic. And it's not going to degrade in a few years. So yeah, I think we should try to recycle these types of plastic. And for that, this sorting is mandatory.
Thank you, Jerry. Joseph has another really good question. Why produce the scanners locally if the components are most probably imported anyway? So why do we have to do all the efforts to start producing it all over the world?
Well, I think an important step in making it locally is that people feel more of a ownership about the product, since they've been involved in the production process and they have a better understanding of the workings or the different components. They are more likely to have to see this product as a high value product, and are more willing to try to repair it if something breaks. If you just get it and it breaks and you don't know what broke, then it's more likely that you will just toss it. If you made it yourself, it's more valuable. That's also a reason.
So it's not only handing over a product, but also the whole capacity and the mindset and the commitment.
Yeah. And there's a lot of these maker spaces and fab labs around the world that show you that are able to produce such devices. So I made sure that it's possible to make it there with 3D printers and basic soldering iron. And yeah, one of these places was the Fab Lab in Bhutan I had contact with, just to know what type of tools they have and make sure that it's really possible to implement it there.
Cool. Well, we have last 4 questions to go, and then we stop because we can do it otherwise in the after. It says, Maxim, he's asking you, do you have any plans to introduce your device, not only in low resource settings, but also, for example, here in high schools? I think it can be very perfect plan to do so. Well done, Jerry. But so maybe we can start also scaling up here and bring the price down by starting to produce them for application here in schools.
Yeah. So I try to make it as versatile as possible. And I wanted to have this low and middle income countries as a sort of set point that at least for certain they can build it. But you are very right. It would be great to see this implemented in other applications, things that I wouldn't have expected in the beginning. But I think this can really help with the education around types of plastic and how plastic can be recycled and how this recycling process is. So it would be very beneficial for schools.
I think it would help to bring the price down, because maybe then we can sell 100 to schools here or 100 to schools, and then we could help the rest of the world to bring down the price of the sensors. Peter van Wij, also well known, also a very hands-on IT guy with impact. Hi, Peter. Very great presentation, Jerry. How does the technology of your scanner compare to the kind of technology used in the Dutch plastic recycling factories? He gives an example, P&D container waste recycling. So how is the performance of this when you would compare it to what we use here?
Well, what you see in the plastic recycling in the Netherlands with the PMD containers is that this is moved to a central factory. And there you see multiple sorting methods chained to each other to, as quickly as possible, sort all of this plastic. But what is a key difference is that often there, the amount of plastic inflow is known, and there's only a certain types. So you can just have a conveyor belt that keeps inputting, and for that you can really optimize these sensors to have it high speed and just spit it out with, for example, compressed air. So it's a very known setting. And that's why the scanners used in the Netherlands are more accurate and faster. But still, it's a specific use case of these types of sensors. But these kind of sensors are used in plastic recycling in the Netherlands.
Thank you, Jerry. We go to the last two ones. Tom is asking, hi, Jerry. Thanks for the presentation. Can the scanner also distinguish the different plastics independent of processing techniques, like between injection molding, blow molding? In these plastics are similar, they are not the same. So can you go also that deeper layer? So you distinguish plastics, but can you also distinguish then beyond that what type of production method has been used?
So great questions from a plastic background person. It's totally correct, and there are limitations to the scanner. So at the moment, it can distinguish these types of plastic, but indeed, often there are additives added to the plastic. So, for example, flame retardants or other additives to make it either cheaper or more malleable. And Raman spectrometers, which use the same technology, but they are more precise, can distinguish different additives added to the plastic. And based on that, probably you can also derive the type of production method. But since this sensor only uses 8 measurement points along this line, it's less accurate. Accurate enough for this application, but not accurate enough to distinguish the additives and the processing methods.
Thank you. And then last but not least, from Jose, I think these from your friends from Open Source, Open Hardware. Jerry, do you think citizens can learn more about IoT, hardware design, machine learning, and technology with your ecosystem? Or do they need a lot of background and training? So on one hand, is it adding? Do we learn more from your project, we as citizens? And maybe the second question, like how much do you need to step into your thing? Can I step into it or not?
It's a good question. So I tried to make it as simple as possible to build and implement. For the manufacturing, you need soldering iron and some patience. And for the software side, it is mandatory to have some prior knowledge, but I try to keep it as open and accessible as possible by using, for example, Python, which is a very easy to understand programming language. And all the information is online. So ultimately, you only need to click download this script and execute it, and then your plastic scanner starts working. If you then want to make contributions to the project, then it would need a bit more understanding of the technical flow of the software. In theory, it's not too complex, but yeah, you do need some programming knowledge.
Thank you very much, Jerry. Thank you very much. Again, you can open it, otherwise the mute for everybody, or otherwise I will be again the only one who will make noise. Yay! Well, also thank you to the audience, because I think it was the longest, but also one of the most interesting Q&A sessions we ever had. So it seems that we have a lot of experts, but also a lot of people who are dedicated and interested in this topic. So I definitely believe that there will be a lot of next steps in this project. So normally we will surprise Jerry a little bit, because normally we would have now a closed session in which we do an evaluation. That means in this case, Jo and me. But sometimes you don't have to take a lot of time to evaluate kind of stuff. And so we did the evaluation beforehand already, Jerry. Oh. So we continue directly to the next ceremony. That means because otherwise the audience have to go out and to come back. And that slows down the whole celebration. So I think you already can hear a little bit some small excitement in my words from the beginning on already. And it has been really a great pleasure to work with Jerry in all the kind of projects we have been working on, and especially, of course, his graduation project. And of course, we hope to still be in touch for several follow-up projects, his own projects, but maybe also other projects in the future. And like you have seen, Jerry has a lot. He's very curious. He wants to learn a lot of things. But he's also really interested not only in technology, but also the context. Who are those people who use it? For what kind of purpose? And I think that makes a real industrial designer, to make that match between technology and the real world, the people, the ecosystem you have to build up around it. But he also likes to experiment. He's not the guy who says, this is a calculation, then it should work. But he wants to prove it and prove it and prove it and experiment until it really works. And then, of course, he also will be very proud to share that with the rest of the world. But he's also a person who likes to reflect on himself, but also on technology, what to do with it, and to think all the time, how can we contribute as designers with technology to make it a better world? And last but not least, we have the idea to make impact, either to educate, to create capacity, to share things, but also, in this case, to recycle more plastic. Jerry, saying that, now he's always getting a little bit nervous. So he was not nervous at all until now. By the way, he feels at home in this place at the moment, because he's walking around on his socks. It's like if it's his own student room at the moment here. So that's a good sign that after these years, you really feel at home in our school. But Jo and I decided to give you a 9, which means that you will get a cum laude.
Wow, thanks.
Woo! So, but that means that, but everybody can clap, but it has no value until we did that signing part of the ceremony, because without signing, there is no Master of Science, neither a cum laude. So, Jerry, you have to find a place now where you can sign. You did not expect that it would go this fast, but we thought it'd make it.
Not at all.
This is like a nice celebration. It goes directly in the whole train of happiness.
Oh, cool.
So, maybe you cannot even, you still have to digest it that you have a cum laude. But meanwhile, you have to find a place where you will sign.
Okay. I think it will be here. I need to get a pen.
You have to find a pen.
Always on hand, sort of.
Yeah. Hopefully. So is the camera focused on there, Jerry? Otherwise, people don't see it. So this camera?
Let's see if we can change it a bit. Whoa.
Yeah, you take your time. We have time. I just have to stay on the 1.5 meter. That's my only thing I have to take care of.
That's even better. The camera has a remote control. But no zoom, I think. Oh, wait, maybe there's... Oh, it even has zoom. Yeah. Okay, I think we're now pretty certain that people can see if I sign it. Yeah. Cool. Yeah. Okay, yes, I was not expecting this.
No. But celebrations are celebrations. Yeah. We can extend it or not, but we already had a lot of discussions, and Jo and I, we did it before. So.
Oh, cool.
So I first have to check if the right person here, because there are a lot of Jerry de Vos in the world. So you have here Jerry de Vos, born on December 9, 1993 in Groningen, the Netherlands, here in front of us. Yes?
Yeah.
Okay. Let me see which one I will do first. We will first sign on this side.
Ooh, cool. Oh yeah. Yeah.
Bij signing this, Jerry became een ingenieur in het industrieel ontwerpen aan de faculteit van het industrieel ontwerpen aan de Technische Universiteit Delft in Delft. And now by turning it around, Jerry, you can sign it one more time.
Oh.
Ta-ta-ta-da, ta-ta-ta-da. And with that, Jerry also became a Master of Science in Integrated Product Design at the Faculty of Industrial Design and Engineering, Delft University of Technology, Delft, the Netherlands. Congratulations, new young Master in Science, cum laude.
Yeah.
So I don't know if Yo still wants to say also one or two words. If you can give Yo maybe I don't know if Yo didn't ask him, but Yo, do you want to say one or two words as the other supervisor?
Of course, JC and Jerry, because it's a very, very, very happy moment. As you know, I live quite close to Groningen, and I send my best wishes to you from Groningen, Jerry.
Oh, cool.
May I say, I'm a rather old man, and I have had many masters delivered already, and you are somewhere close up to the 300th master.
Oh, geez.
Yet I can tell, my machine learning has progressed already a little bit, and I can tell you are among the best 10% or so of my students ever, and you did a remarkable job. And you were putting forward that you only contributed a small part to the solution, yet a vital part, a very important part. And many vital parts together make the whole solution. And you really, let's say, distinguished yourself in this research. You really earned the cum laude. Many congratulations. Also extending it to your family, to your friends. You must be very, very, very proud about Jerry. We are proud too, but family, friends, you must be even more proud. Thank you, Jerry, for working together, and I hope we keep in touch.
Cool. Thank you, Yo. Thank you.
So that means that you are a free man. You are not anymore a student. You are going into the even bigger world. I see a lot of happy people there on the screen. I see happy and proud parents, but also a lot of other friends. Jerry, the last few words are yours. You didn't prepare for that so fast, but sorry for that. But I thought this would be nice to make it directly a big celebration.
Yeah. Thanks so much for all the supervising and the help, especially, without your knowledge and Joe's knowledge, there wouldn't be any theoretical background. It would be just a lot of prototype, but no real foundation. So that helped a lot. Thanks so much for that. Thanks to all the friends and family for all the patience. And I'm slightly have neglected maybe some and didn't pay a lot of interest because I was working on this thing. And thanks also all the other people like Armin who started the Riri meter, which inspired the project. And I think Dave is there and Joseph from Precious Plastic and some people from the Ocean Cleanup. So that's super cool that everybody could make it today and took an interest in my thesis. So I'm super honored. Thanks a lot.
Thank you. Yeah. So the official part is over. My job is done. The job of Yo is done. The real world can take it over, and we give it to the big world. And we will still see how we can support the ideas of Jerry in the future. But for now, I think it's time to relax and to celebrate it with friends and family. Yeah. In whatever way you will do that. Mm-hmm. It's a good weather, so it's nice time to celebrate it. And
Cool. Yeah. Thanks. Thanks, everybody.